Hello and welcome to the Chapter 6 podcast on Section 6.3. Today we're going to talk about line spectra and the Bohr model. So spectra, these are basically radiation broken down into the different wavelength components. For instance, white light is what we call a continuous spectrum. It's a rainbow of colors consisting of light of all wavelengths. However, if we go back to our flame test and if we actually took the light we saw and ran it through a spectrum, it would be what we call a line spectrum, and what we would see is that only certain wavelengths are actually present in those different colors we saw. And if we actually look at this line spectrum from each element has its own unique line spectrum. So we're able to use that as one means of identifying elements in unknown compounds, as well as in the lab, as well as things in space as well. The line spectra. We're going to talk about hydrogen first, and we'll kind of get to why in a moment. But Balmer and his lines for hydrogen follow what we call the Balmer series. The simple formula is just using Planck's equation more or less. Rydberg, however, showed that there are other spectrum bands for hydrogen that show up in the non-visible range. More specifically, the ultraviolet and infrared regions. So if we want to know the frequency of these, we would use this equation here, where it's kind of a complicated equation, but basically what it is, it's 1 over the wavelength. RH is the Rydberg constant, which is listed below, and then this represents the difference in quantum level, so a change from a ground state to the excited state. And remember, N represent principal energy levels, and these are energy levels where electrons are likely to be present, and these are always whole numbers. And we'll get more into what N is in a little bit. Bohr's model is probably best known as the planetary model, and basically he used the planetary model to explain the line spectrums of hydrogen. So in other words, he looked at the way electrons, the energy patterns hydrogen would give off, and he used that to try and model what all elements were doing in terms of their electron arrangement. The idea here is if he could unlock hydrogen's electron arrangement, he could apply that model to other elements. So these were the 3 postulates he kind of came up with. Number 1, only orbits of certain radii corresponding to a certain definite energy is permitted to the electron in a hydrogen atom. So he believed that they were like electrons were orbiting the nucleus in the same way like the planets orbit the sun. An electron in a permitted orbit has a specific energy and is a allowed energy state. The electron is an allowed energy state, will not radiate energy, and therefore not spiral into the nucleus. So in other words, the energy state keeps the electron a fixed distance away from the nucleus. Okay. The other thing is that it's always the same distance. It cannot move around, and the space between levels is well defined, and there's no possibility of having electrons in between these orbits. 3, energies emitted or absorbed by the electron only as the electron changes from one allowable energy state to another. So in other words, if an electron is excited and leaves its original orbit and goes to another orbit, it will always be in the form of E equals hv. Okay. So here what we show here is the energy states of the hydrogen atom. So if this is the principal energy level, like we have the nucleus, then we have energy level 1, 2, 3, and so on. You'll notice that the distances between the principal energy levels starts to shorten the further away from the nucleus you get. And these distances that you see here correspond to the energy of the photon that's given off as these electrons go from one principal energy level back down to another one. Okay. And these different colors represent the different kinds of energy that are given off. Some of these are in the form of color light, some of these are UV and ultraviolet light. Ultraviolet and infrared, sorry. The energy states are we can use this equation. So it's Planck's constant times the speed of light times Rydberg's constant times 1 over the square of the principal energy level. And instead of just using individual numbers, they just kind of multiply them all together and you get this. And the principal quantum number, again, is a whole number always. The ground state is the lowest energy state. This is where we will always begin, where electrons will start. And the excited energy state is basically anything above level 1. And we can actually use these, and we can actually quantify if we subtract the differences in energy from level 1 to level 2, we can anticipate and quantify the amount of energy given off by by these quantized electrons. So again, the idea here is that electrons can jump from one allowable energy state to another, and we can quantify this again. And this will be equal to HV because, again, they have to follow this. And because of this, because we can relate that equation from before to Planck's equation, this is how we know that specific frequencies can be absorbed, only certain ones. Okay? And then all this is here is a derivation of our equation. So we can use Planck's equation, and we can use our difference in energy equation, and we can rederive the Rydberg equation. So this is kind of where his more complicated equation to explain what the non-visible forms of energy were how they could identify their wavelength and frequency. However, as successful as they were with explaining Bohr's the hydrogen atom's behavior, when they try to apply this to other elements, most of what he postulated with hydrogen didn't work for any other elements. His big mistake was the path around the nucleus. You also have to remember that this whole idea of quantum and moving away from traditional Newtonian physics was happening at the exact same time. So it's, he was kind of a victim of his success, but also a victim of the field emerging at the same time as he was working on electrons. But he had two very important points, despite his model being incorrect. He did show electrons can only be in certain energy levels, which are described by quantum numbers, and that energy is involved when an electron moves from one energy level to another one. So, like, he was able to show, that these energy levels were only certain ones were allowable, which, if you think about it, does apply to other elements. It's just that the way the way he was defining their position was a little bit incorrect, more or less. But he did get some things right. And the people who kind of moved beyond Bohr took the things he did correct and then built upon it. And that's kind of what science is all about. We create models. Sometimes they're limited by imagination or technology. And then as those things catch up, we change the model and then we move on and it becomes a more complete picture of what it is we're trying to understand. And that's it for now.